Hello everyone to YouTube channel Explore Math Together, and I want to start off the question, what do you think in your opinion the hardest way to make a $1 million? In my opinion, it's like solving one of the Math Clay Institute problems, which one of them is Riemann hypothesis. Hypothesis which we will talk about in this episode. If someone has a courage and a knowledge, of course, to solve that problem, the prize is $1 million. So as we saw in the previous episodes, the Euler's product formula, which gave us an understanding that all numbers are connected to prime numbers, and the sum of all numbers is the product of the prime numbers. So, however, in the last episodes, we mostly viewed when s is greater or equal to 1. However, we didn't have really chance to see when s is smaller than 1, or even when s is complex number. And that's why we have a Riemann hypothesis, which explores this zeta function in terms of complex numbers. And we will see later how the zeta function is connected to a Riemann hypothesis and what you need to prove in order to get the $1 million prize. We already know that when s is greater than 1, our zeta function always converges to some numbers, even if the complex part, the real part of the complex part is greater than 1, it always converges to something. For example, when s is equals to 2, as we see when we plug 2 instead of s in our formula, in our zeta function, our function always converges to pi squared over 6. However, it never reaches 2. From previous episodes, we already saw that when s is equals to 1, we just get our series, which is also converges to something. However, the interesting part is when s is equals to -1 or to other negative numbers, it turns out that this will get us a harmonic series. And in fact, like if we see it from the first sight, it doesn't make any sense as the series diverges. It just goes to infinity. So the rule is simple. When s is greater than 1, the zeta function converges. When s is less than or equal to 1, the function only works in the specific region. However, Riemann had a radical idea that what if s is not smaller than 1 or greater than 1, but it's a complex. So as we've seen from previous, this is the complex number formula where this is sigma, the real part, and tit is the complex part. So let's take an example. Let's say that s is equals to 2 plus I, the complex number with the real part 2 and imaginary part 1. When we had s is equal to 2, as we saw previously, the function just converged to pi squared over 6 in a straight line. But when s is equals to 2 plus 1, when we add the complex part, something kind of beautiful happens here. Each term in the sum now has an imaginary component, and the imaginary power creates a rotation. Each term rotates by different amount and different directions, which makes it kind of complex. However, it's at the same time something magnificent. When you add them up, they spiral around in the complex plane. They go around it. But here's the key. The real part, which is 2, still makes the term shrink. So even though they are rotating, they are getting smaller and smaller. The spiral wins tighter and tighter, eventually converging to a single complex number. So to summarize here the complex part is that even when we have a complex number and our real number in the complex function is greater than 1, it has still the same principle as we saw earlier. The function still converges. However, when we take the complex function and we plug the real part smaller than 1, and it doesn't converge anymore. However, the infinite sum always diverges. For example, when we plug -1, as we saw earlier, the zeta function takes the form of harmonic series. And you just see that it's the sum of infinite positive integer, which when we see at first doesn't really make any sense. We can just say that, okay, we can deduce here that the function only works for the real number greater than 1. End of story? No. If we think as Riemann, because Riemann asked himself, what if we could extend this function? What if there's a way to give it values when the real part is smaller than 1. However, the thing is here that we can't put just any number smaller than 1 into the zeta function. What Riemann came up to is that only those numbers which will have a derivative can be plugged into the zeta function, and it will make sense, and this will called analytic continuation. As you see, this beautiful graph that we have is part of the analytic continuation. The complex functions that have derivative everywhere are called analytic. And here's the beautiful thing. It turns out there is only one way to extend the zeta function that keeps it analytic everywhere. The process, as we said earlier, is called the analytic continuation. Using advanced technique, Riemann was able to extend the function to all complex numbers. And this is where it gets interesting and where we are already very close to understanding the meaning of the Riemann hypothesis. So when we have the graph and all those intersections, we just need to know when does the graph intersect the origin, when it equals to 0. In other words, for which value of s does the zeta function equals to 0. Now we know some obvious zeros. As you said earlier, they're called trivial zeros, which are the negative even numbers. They are -2, -4, -6, and so on. These are, as we call, trivial zeros. However, the thing that we also talked on the last episodes, we need to find the non-trivial zeros. That's where the Riemann hypothesis is, that we know about the trivial zeros, that they are equal to 0. However, what about the non-trivial zeros? What about those numbers that are not negative, that are greater than 0? And Riemann was able to find that there are the numbers that are also equal to 0, as we said, the non-trivial zeros. And these zeros live in a region called the critical strip, where the real part s is between 0 and 1. The yellow shaded part is what we call that critical strip. However, what's amazing, that these zeros contain deep information about the prime numbers. The location of these zeros is intimately connected to how primes are distributed. That's the most magnificent part of the critical strip. The other question, I know there's a lot of question arising from all this, but however, I'm saying that it's totally worth it. The topic is really engaging, and if we see there's a lot of new things that we can get from it. So back to the topic is that the non-trivial zeros, Riemann was able to deduce that they are all located on a single vertical line, and that line is equal to 1/2 on the graph. The line is called the critical line, and the Riemann hypothesis that all non-trivial zeros of the zeta function lie on this critical line. As we saw, the critical line along our Professor Riemann, it's the line which is in the yellow shade in the critical strip, and along that line all the numbers are the zeros of the function. However, we are already there, guys. What is the Riemann hypothesis? What you need to prove or disprove is that in that line there are infinite trillions of numbers that the computers and people found which can be equal to 0. However, we still don't know that all the numbers in that line are the zeros of the function. That's what we need to prove. Is it true that all those numbers are equal to 0? Is there a certain way to know for sure? Or if we can disprove, if we can find a certain number or certain series of numbers on that line which are not equal to zeros, then we will find the solution to the Riemann hypothesis. So why does really the Riemann hypothesis matters? Why we need to think about it, why we need to study it, why someone needs to prove it? The answer is that mathematicians have tried to solve it for hundreds of years, for 100 years, and they came up to other hundreds of theorems which were based on that assumption that the Riemann hypothesis is true. So which means that if someone proves it, all those theorems become absolute truth. If someone disproves it, mathematics will have to be rewritten in different other theorems. So guys, we finally arrived to it. We finally understand what does the Riemann hypothesis means. When I started really this YouTube channel in the first episodes, first 2, 3, I really didn't understand what I'm doing. As you know, I'm a student at UWC East Africa, and I'm doing my research paper also on this hypothesis. It's really interesting. It gives you an really deep insight in mathematical world. Doesn't need to you don't need to have a deep knowledge about higher mathematical level, just curiosity and just like I also understood this theorem by watching YouTube videos, by reading some small articles, and it's really engaging if you have some interest in those parts. So guys, I really encourage you to, if you didn't understand from my YouTube episodes, watch others such as 3 Blue 1 Brown or Number Field, are very great YouTube channels which gives a lot more information about the hypothesis. And yeah, thank you guys. We will see other topics. Maybe we will start exploring AI or programming or maybe physics or other part of sciences. I don't know yet. I will come with other interesting topic which engages me and which I will think that you guys will also be interested in. And we'll see you later.